The spice is going to be that high. Are you someone like that? Yeah. Check that. He goes before quiz. Yeah, those are the quiz and the quizzes are usually they're absolutely one for some problems. Like, but this out like 10 minutes before the class.
He goes over he'll go over a practice problem. And we will tune it out. And just sign the attendance because we don't want to get an email. Hey, why did you leave class?
He might even if you played the technical piece on it was one of the simplest examples possible. And then there's a fucking inductor and a fucking
Okay, good morning, everybody. As you guys had a good discussion. Okay, so we're going to continue. So today we're going to cover, first of all, we're going to cover the T model. And last time I mentioned that the pi model, look like a upside down pi with a MOSFET and PGT, and they work great in many scenarios. However, when you get to certain amplifiers, that pi model can get your mathematical calculation very complicated. I mean, you can still work it out. It's just that it's more complex than what you would like to. So we're going to go over the T model. We'll start with MOSFET, and then we're going to also look at the T model of a BJT. And then by that point, I think we're going to go through one or two examples that will be offered today. And of course, if you look at the content of this chapter, and then a lot of repetition from the discussions, like with next section, we talk about the different configurations. You're going to see again like a common source amplifier or common emitter amplifier, which I already discussed many times, but just sort of give you a systematic analysis on those different amplifier types. And then we talk a little bit about biasing. And then finally, we again go back, review the different discrete amplifiers and how they work. Okay, so let's start it by looking at the pi model of a MOSFET. If you guys remember the MOSFET amplifier, again, we're going to start with, oops, today is black. I guess I just don't have a choice to select the color. Hopefully it's okay. I don't mind what color, but just sometimes it, we're going to start with the MOSFET, the simple MOSFET model. Here, you notice that I already eliminated the DC biasing. Just think that you do have a DC biasing there, but for AC, we don't need it, so I just remove that. And if you guys remember, the pi model that we derived was simply, and we can include that RO or the early resistance right now, or we can include it later. It really doesn't matter. But let's do that later so that it doesn't really. So this is our MOSFET model in the T model. And if you connect, like what we said was, if you find any circuit that has a MOSFET or BJT in it, go there, grab that component, like take it out and replace it with a small signal model, and then solve the circuit based on the components that are connected to the small signal model. So this pi model is perfect, as we said, for MOSFET at like the common source amplifier. But as I said, if you have something, let's say in the emitter or in the source, and you will be having trouble because all of a sudden your VGS is no longer input because your VGS is difference between input and the voltage at source. But now you have a resistance, therefore you do have a voltage at source. So now it's kind of, you need a couple equations to manipulate in order to get the actual expression for your output. Right? So in that case, you would find that the pi model that we're going to derive today is very useful. So let's go ahead to look at what happened with the pi model. So we're going to start with the pi model, very simple pi model. So what we're going to do is we're saying, well, this is the current source. Oops. I cannot erase this one. Okay, that's fine. Interesting. So this is the current source. So we add another current source in series with the current source. So you think about it, you have a couple current sources in series, what happens? Nothing changes, right? Because it's just current source. But what's important at this point is that, well, if we create a current source, remember, if the source is grounded in this example. Now you have current source, and it is possible that we can create a voltage at this point over here, between the two current source, and we could create a voltage here. Let's call it Vx, and we could create a Vx that is equal to Vg. I mean, this again artificially. There's no certain thing as you create one, but just that if you create a couple current sources in series, then you will be able to create a voltage at that point, because the voltage of current source is really random. It depends on the other circuits, it's not depending on the current itself. It depends on what else is connected in the circuit. So if that is Vx is the same as Vge, which means they have the same potential, so ultimately we can connect this to terminal. Without creating some trouble. So again, this is again still GM times VGS, or VGS, let's call it VGS.
Which one is GM-VGS?
Both are GM times VGS. It's the same current source. So now what we have done is we connected the gate to some artificial point that we created. Oops. So we just created and we connected this together. It doesn't change anything because we knew that we created the voltage at that point, which is equal to VGS. So nothing really changes the meaning of the circuit. But what's important at this point is that we can street some lines, just make it look a little bit different. So what we're doing is we're going to move the current source on the right hand. So instead of having them like a flat and this, and we just move them around to form that circuit. Now you see this circuit is identical of this circuit. We just changed the view. We didn't change the configuration of the circuit. So both current are equal to GM times VGS. Now, what's important? What's important at this point? You understand there's a voltage between G and S, right? So if you look back at the circuit, this is VGS. So which means from here to here is VGS. So what you're saying is that this is the current source, which is the controlled current source, which is GM times VGS, and the voltage across this current source is also VGS. What do you mean? Well, I mean, what does it mean to us? Well, what we're saying, yeah, if we use VGS divided by, if we use VGS divided by GM times VGS, So which is voltage divided by current. What do you get? You got a resistance. So we're going to give a definition called this resistance of RS. And this RS apparently equal to, you cancel that VGS, equal to 1 over GM. So this is where we really get a beautiful equivalent circuit, is that, well, that's really simple equivalent circuit. So now we have found the circuit. We call this a T model. It's actually, I mean, if you look at a T, it's like a slanted T. It's not this T, but if you look at this way, if you rotate it by 90 degrees, it looks like a T. So they call this a T model. So in the T model, the key point is that you still have to calculate GM, but you can calculate RS, which RS is 1 over GM. So that really simplifies. Yes, go ahead.
No, like gates, there's no like gate, current.
Well, there's no current. That's right. Well, yeah, I probably didn't mention. You see, there's no current because those two currents are equal to each other, right? So there's no current coming from the gate because the current from up, down is the same current.
Oh, this is a MOSFET.
Yeah, this is a MOSFET, right? There's no current. So there's still no current from gate to source. Well, you might say, okay, why does that help? So we can look at we can look at this circuit over here. This has RS at the source, right? So how do you draw the equivalent circuit? As I said before, if you draw the equivalent circuit, you have a resistance over here, and your VGS is here. You see, often what our students make mistake in the beginning is that they look at the VGS, they get the input V in, they say V in is VGS, but that's not true anymore because your VGS is between G and S, your V in is between gate and the ground. So there's voltage drop over here. That's very important to distinguish, right? So if we have a T model, it could make it simpler. Let's see if actually that would happen. Okay, so again, we're gonna take the MOSFET out and we're gonna draw the equivalent circuit of the MOSFET first. Yeah, we're only doing the small signals, right? So,
Does the top become ground?
well, you tell me. So the top is your drain, and this side is your gate, and bottom is your S. So this is your lowercase rs, this is your GM times VGS. Now we have to find what VGS is just in a little bit. So now tell me, what is connected to gate? You know, this is the first step, is take the MOSFET out, draw a small equivalent circuit, and then the second step is to find what components are connected to each terminal. So from that circuit over there, what is connected to the gate? Now, neglecting DC, just look at small signal. That's the voltage source, right? So we have voltage source connected, which in this case, we're going to call it V in. So we're not going to call it VGS anymore because that is your input. That may not necessarily same as V in, same as VGS, okay? Okay, second, what is connected to the drain? Resistor, and to where? Ground, right? Okay, so to ground, and of course all output is over here. Let me mark all output. Now in this circuit, actually, because it got a resistance at the source, you can get your output either at the drain or you can get output at source too. But you know, in this case, we're going to get output at the wheel. So our RD is connected to ground, because the voltage source, again, the DC voltage supply is a ground for AC. So we have RD over here. Okay, last one, what is connected to the source? Through a resistor to ground, which this resistor is capital RS. So on this circuit, where do we mark our VGS?
This is the voltage across RS.
Oh, it doesn't go away. So your VGS is the voltage from gate to source. So this is your source. And this is your drain. Okay. So you see here, clearly V in is not VGS. That's important. If you treat V in as a VGS, you're almost totally wrong for this output. Okay, you might say, oh, why does this make it simpler? Well, if you look at this one here, is ground.
Yeah, so voltage divider.
No, it's actually, well, you can say it's a voltage divider, right? So your VGS is going here this way,
And the voltage at.
and the voltage at these two are going to be divided.
We can find the voltage at S and then subtract V.
You can find RS first, from GM, you can find RS and find RS. So your VGS here and your V in is across this pulse resistance. So you got that. Now you got that VGS and you have VGM times GM times VGS, you got the current. Now use this current multiplied by your resistance, you got the output. So that's fairly simple. But if you do the previous circuit with the pi model, you're going to have to solve for a pretty complex nodal analysis. Yeah.
So our current is coming from the ground to DC.
Your current is coming from, well, yeah, you're coming from ground to RD and so here and all the way here and all the way here to ground. And your current also, coming here. So, yeah, but there's no current here because this current is the same as the current over here. So that's a kind of interesting phenomenon because, I mean,
Because there's no resistance.
yeah, well,
So there's
right, there's no
reconnect.
there's no resistance here, right? Yeah. So this is a very interesting, very useful process to do that. So here, apparently, this is what there was actual process that you can follow. We already discussed that. And if you want to add the RO, well, often that we do if we are given VA, the early voltage, and we would add RO, which is across drain and source. So another mistake sometimes our students make is that they accidentally add the resistance between gate and source instead. So, or between drain and gate instead from, remember this resistance is across drain and source, right? So, but the problem sometimes is that when you add RO, this T model is not that useful anymore because like if you like go back to our previous example, if we add that RO, so that RO will be between here and here. So that will make your problem actually quite difficult because now you got another node and we have to calculate how much current going here. These two are no longer voltage divider. So you might want actually to switch back to your pi model. So it all depends on the complexity of the circuit, the configuration of the circuit. We might choose the pi model or T model. It will really depend. Okay, so now we're going to go to an example. This example is perfect example to use the T model. Probably for now, because this is already a equivalent circuit drawing for you guys. But for now, just look at the circuit on this left hand. As we discussed last week, you guys already know what happens to the capacitance right, at for a small signal. They all become like short circuits. The other thing to notice that the gate is grounded. So the input is not at the gate. Where's the input? You guys see where's the input?
Input is at our
So yeah, so your input is at your source. Your input at your source. And another interesting thing to notice that there's a DC current. And often this we call it like a current source or current mirror. So we build this using the other circuits. But over here we use like ideal current source, which is a DC current. You know, when you see this is a DC current. So when there's a DC current there for small signal, what happens to a DC source? It becomes an open circuit. It becomes an open circuit. So that's why we can start to draw the small signal equivalent circuit. Now, this also tells you to neglect the channel length effect, which means neglect RO. So what I'm going to do is I'm going to redraw the circuit over here so that we can work it all together step by step. So you guys get a better understanding how this works. You know, over this here. So I can redraw the circuit. So the circuit is this. So what I'm going to do is I'm going to get rid of all the capacitors so that we don't have to look at them anymore. Oops. Okay. So I did remove the capacitors so that we don't have them here. There's also a ground. So the only difference that I think what you guys make sure that we really have an arrow here, which means this current source is pointing to like a lower voltage than ground. Because if you have ground here, you see there's a ground here, there's a ground here. So it's typically impossible to have current flowing between two grounds, have a current source. So this voltage got to be lower. So so this is a negative voltage. But anyway, so by looking at this circuit, first of all, because input is at the source, so likely the pi model is not going to work very well. So that's why we're going to go with the T model. So the first step is let's take out the MOSFET and draw the T model for the MOSFET. And then step 2, we connect all the components. Step 3, we solve the problem. So the MOSFET is right over here. So we're going to take out the MOSFET. We're going to draw the small signal equivalent circuit model. This is our gate. This is our TM. So we take out the MOSFET step. You know, you guys in the future always do this. Look at the MOSFET, draw small signal model. Okay. Step 2, connect components to each terminal. Well, we start with the gate. Where is the gate connected? So gate is grounded. And then we're going to look at the drain. What is connected to the drain? A resistor, and then to ground. And all output is over here, okay? Okay, now what is connected to the source then? Well, first of all, there is an input. And secondly, there is a DC current, which becomes an open circuit. So now you get this a quite nice circuit. Now, at the bottom, you don't have to do that little like change, you know, this direction right over here, since this is down here anyway. So I'm just gonna draw the input over here. So where is our VGS? Okay. Your VGS is, I mean, first of all, what I was asking is that where do you mark your VGS?
Across the resistor.
Yeah, it's across the resistor RS. So this is important because you don't treat saying, okay, VGS equal to VI, actually it's not, right? So VGS is from gate to source. The reason is your source is right in the middle here. Your drain is at the top. So your source is not at the ground, right? Okay.
VI equals, VGS equals negative VI.
Yeah, so in this case, we need to find out what VGS is. And if we find VGS, we can find GM times VGS, the current, and then we can find VO. So basically, you can start writing, okay, if I got VO equal to minus GM times VGS times RD, that's our output voltage. But, you need to calculate GM, of course, but we need also to find VGS. So if you look at VGS, right at this point is your negative point, is a VGS. But from here to here, there are two grounds. So basically, this is a little loop. And from middle point to ground, that's VI. And from middle point to ground, that's negative VGS. So your VGS is negative VI. So your VGS is negative VI. So now you plug in this one to here, you get VO equal to GM RD times VI. Or in other words, you can get your gain, it's going to be VO over VI equal to GM times RD. Yes? The current source is the DC current source. DC current source is the open circuit for small signal. When we like always treat this as doing superpositions. The small signal is a superposition, is a circuit with the small signal superposed on the DC signal. So DC is open circuit for current. Voltage is short circuit, like VDD is becoming a ground. Current source becomes open. Yeah. In small signal, the DC current is open source. It's open circuit. DC current is open circuit. And DC voltage is a short circuit.
It's like we're taking the superposition,
Yeah, it's like you're taking superposition, right?
treat all current sources as open and
All DC current is open. If it's an AC, of course, it's not open. All DC current, yeah.
Well, when you're doing superposition.
Yeah.
When we're talking small signal, we're talking only.
One signal, yeah.
We're talking about the AC component.
Yeah.
So we're taking a superposition of only the AC components.
Right.
So in superposition, all current sources, when you're ignoring the current source, all current sources become opens and all voltage sources become wires.
Yeah. Okay, so this is what we get. Of course, if you want to get the numerical value, you can go back to look at what GM is. GM is well, to find the GM, we have to also solve for the DC biasing currents, like find the ID and so on. So we're probably going to skip those steps, and you guys can do the mathematics. So we did that pi model already for BJTs. So I think I'm going to skip a couple of slides because we did that. I can probably recall the things that we did. Is like what we did was we said IC equal to ISE to the power VB over VT, and then your IC equal to ISE to the power VB plus beta VB over VT. And then you extend this one and you use E to the VB over VT equal to approximately equal to 1 plus VBE over VT. And you plug in this back, you get sort of, eventually we got the, we also got the GM and then we got the pi model, things like that. But we also find ways to calculate R pi. Okay, so today what we're going to do is we're not going to derive that anymore because we did that, as I said. What we're going to do is to look at how to get from this pi model to T model. Now in this pi model, first of all, we derived it without RO, with the early voltage, without early resistance. And we have this This one is more like popular to use. And this one is exactly the same circuit, but instead using VBE, we use IB. So you see here, it's times IB instead, right? That's actually identical circuits. So you don't have to worry about that. So when you get IB, really this better times IB instead of GM times VBE. Now these two equations, guys, write this down. Always, try to know where to find those equations because when you get a numerical value, you always have to go back to refer to these equations. Now, once we have RO, we just simply add RO between collector and emitter. That'll give you our circuit that's more accurate circuit considering the early effect. So this is what we have, adding RO into that circuit. And that RO can be calculated using VA or divided by IC. That's what we did in the DC analysis in chapter 6. Right? So what I'm going to do is, based on this small signal circuit, we're going to go through the same process to derive the T model. So we're going to use this one to start with. We're going to we can keep RO, we can add RO later. I mean, it really doesn't matter. We're probably going to skip RO for now because, I mean, it's just something added on these two terminals. You can always add it afterwards. So let's start with without RO. So let's, why is that? Why is it doesn't? Okay, well, this goes. So so that's your typical pi model. What we are doing is going to do the same thing as what we did with the MOSFET. So we're going to add another current source. As we said before, if you add a current source onto that branch, it doesn't change mathematically. I mean, even physically, you can do that. You just can add a couple current sources as long as they are going to have the same current. You cannot have current sources in series if they don't have the same current. You have them in parallel, but you cannot have them in series. They have to be exactly the same amount of current. So now if we add the current source at the top, it doesn't change the circuit mathematically. So therefore, we can create a voltage, which here is going to be the same. So we create a voltage here, which is going to be the same as VBE. So by doing that, we actually can connect So we do that, it should be fine. Yes, go ahead. If they don't have the same amount of current, that circuit will, because if you have one current, say 1 amp, the other has 2, you put them in series.
It's like plugging in 2 volt sources of different voltages in parallel with each other with no scenes. One will try to charge the other, and
that current has nowhere to flow, so it's just voltage is going to start to increase, and then eventually it's going to break. Yeah. You have a good example. You have a 1.5 volts and you got 9 volts. You can have them in parallel. What happens? The 9 volts is going to charge that 1.5 volts with a huge amount of current because the internal resistance is very small. So now you're going to catch fire. Yeah, it's going to explode. Yeah.
Well, yes. If it's it's a little weirder with current sources, but there isn't much that is equivalent to an ideal current.
Yeah, I mean, in the physical world, we don't have current source, standalone current source.
Well,
There's a voltage source, like battery is a voltage source. You don't have such thing. Say, okay, can you give me a current? No.
Make a voltage difference and then the right amount of current they want to flow through.
well, the one thing that does act like a current source is solar panels, I believe.
No. Solar panel is not a current source. Well, when you add a controller, it act I mean, it could control it like a current source. So naturally, no current source exists. You have to build something to create a current source.
Yeah.
Not like a battery, it's a voltage source. Yeah.
Like, why do we solve the problems if they don't exist in real life?
Well, because we artificially create current sources. And we actually, yeah, I mean, it's very useful. Again, we don't talk it too much in this one, but in next class, you're going to see for every single circuit, you have a current source because you use current source to do the biasing. We usually don't use voltage or resistance to do the biasing. You know, when you go to this IC design, you have millions or billions of transistors on a single chip. It's very difficult to create resistance. Sometimes on a IC design, on the whole like a couple million IC MOSFETs on a single chip, you only have 1 or 2 resistance. That's it.
Okay. Back to the problem,
Yeah.
plug them in parallel to each other, so.
Well, because the current source we put there, it's just artificially we put it there, and we create a voltage between that two, same as VBE. So we now connect them.
Are we going to change it into a resistor?
Yes, we have. Well, that's the purpose. I mean, that's the whole point, right? So okay, so now we have this one equivalent circuit. So what I'm going to do is we're going to look at. We know that there's a voltage from here to here is VBE. So basically, I can get, say, the current, because this is the current. So on the second, there's the 2 branches in parallel. On the left hand, that's R pi. But on the right hand, we know there's equivalent resistance. Let's call it I can't call it RE yet. Let's just call it something like Rx. Rx is going to be the voltage VBE across it divided by Gm times VBE. So that's equal to 1 over Gm. That's equal to 1 over Gm. So that's the equivalent resistance of the right-hand branch in the 2 parallel branches. So what we are doing is, well, since it's equivalent to a resistance, we can put a resistance here instead. And this is what we call Rx. This is called R pi. Now, since Rx and R pi together, I'm going to put them in parallel. So R pi is going to be in parallel with 1 over Gm. Do you guys remember what the equation for R pi? Is it beta over beta over IC?
Yeah, no, beta over Gm.
Oh, beta over Gm. Okay, right. Okay, so this in parallel, which means we can get beta over Gm multiplied by 1 over Gm, and bottom is only beta over Gm plus 1 over, no, yeah, plus. So we multiply Gm, blah, blah, then we got beta over beta plus 1 over Gm, and so that is alpha over Gm. So we call this one Re. Basically, it's going to be And this one, we further draw it like this. And if we add the resistance of the early resistance, then we will have and the one that on top is GM times R is GM times VB, and then the bottom is RE. And the voltage here, VB is right across here. So this is GM times VB. So there's two equivalent circuit also T model. So I think at this point, often that I get asked by students that, well, now you're telling me there's a T model, there's a pi model, and this pi model without RO, this pi model with RO. How do I choose them? When I look at the circuit, I guess the rule of the thumb is that, first of all, if you are given VA, you always include RO. And that's the point, if you're given. Now, if you're not given VA, you don't have to include it. Probably it's going to be wrong if you get the answer with something that you assume RO, just apparently if you're not given, so don't include RO if you're not given VA. Okay, that's like the first thing to decide. And then the second point is that between pi model and T model is you look at the bottom of the transistor, like the source or the emitter. Is there anything there? Is your emitter grounded? Is your source grounded? If your source is grounded, go with pi model. If there's resistance or something at the source, like input or resistance or current, whatever, capacitor, go with your T model. Yeah. So let's move on to, so this is a T model with we derived. And then if you add RO, right? So those are the models. Okay, you guys have that. Now we should have, why do you say it doesn't go away? Can you see? I don't know. Oops. Usually this goes away. Why today doesn't go away? Oh, it does. Okay. So this is example. We want to find the voltage gain. We want to neglect the early effect. Usually we will tell you neglect the early effect, but sometimes it does not say that, but it does not give you VA. So in that case, you can also choose to neglect early effect. Okay. All right. So for this circuit, we want to find the gain, voltage gain. Remember, to find the gain, we usually have to, you always have to find a GM. And then once you find a GM, to find a GM, you have to solve for the DC biasing. So in this example, the first step will be, let's look at the DC biasing, and then look at find a GM, and then from there we draw the equivalent small signal equivalent circuit, and then we use circuit theory to find the output. So this one, the reason that we're looking at this one is there is a resistance. There's resistance connected at the base. So instead of connecting the voltage source directly to the base, we connect a resistor at the base. And actually, this is very common because later on, like in section 3, when we talk about biasing, sometimes we use, if you guys still remember, we talked about last chapter, we use two resistors to bias. There's one up, there's one down. We connect up to the VCC, and we use Thevenin's equivalent circuit to find the equivalent circuit where we have a voltage and we have a resistance, right? So in this case, your gain is not GM times RC. You remember when we have this connect directly to the base, we have GM times RC, right? Or minus GM times RC, the gain, which in this case is not true because you have RBB connect at the base. Okay, so first step, let's do the DC analysis. So to do DC analysis, we would, well, let's go back one more step. Just look at here. So for DC analysis, when you're doing superposition, so what we're doing, we short the voltage source, which in this case is a voltage source, we short it. So we short this one, but this is 3 volts, right? I mean, this is 3 volts at the base. So that's how we draw the circuit. It's 3 volts. So at this point, you guys can see, we assume, now it has to be, so we're gonna assume in active mode. If we do that, we know that the capital VBE is going to be 0.7 volts, which is from here to here. Okay. So from here, we can find current IB is going to be 3 volts minus 0.7 divided by 100K. And that gives you 0.023 milliamps. So this step is important. You know, it's in active mode, the base to emitter voltage drop for DC voltage drop is 0.7 volts. So this assumption can be typically made. If you're not given, just make that assumption and you don't have to worry about it. Okay, so from there we can find IC, which is beta times IB. Beta is given at 100, so that's going to be that's going to be 100 times 0.023, so it's going to be 2.3 milliamps. So at this point, we want to find VC. Now, why do we need to find VC? Because like IC will be enough to calculate the GM and so on. The reason we need to find VC is we want to verify actually this circuit is in active mode. So IC is going to be 10 volts minus 3 kilo ohm times IC. IC is 2.3, so 6.9, 3.1 volts. And 3.1 volts is going to be larger than 0.3. So it is in saturation. It is in saturation. Active, oh, yeah, you're right. Not in saturation, it's in active mode. Sorry about that. I sometimes got confused as well. It is a BJT, it's not a MOSFET. You know, it's how natural to go from MOSFET to BJT and to talk about not the same thing. Okay, so now we find all these outputs from here. You can find RPi, you can find GM, and so on. Let me get the exact value so that we can move on to that. Okay. Yeah, actually, I don't have the exact value calculated, but anyway. So here, once we find GM and RPi, we're going to look at the small signal. So from this small signal model, we simply take out the DC, the DC voltage becomes a short circuit. And if you look at interesting, the top is VCC. They also put a ground, which means it's actually a small signal, so we already grounded. Now we're going to draw the small signal equivalent circuit of the BJT. As I said before, this thing is emitter is grounded. So we're going to use the pi model. And also we're neglecting the early effect. So therefore there's no RO. So we got the equivalent circuit. The middle is our BJT. Our emitter is grounded. Our collector is connected to RC, to ground, and then our RBB is connected to the base, and we have R pi. So from here, the only thing that we need to mark out is we need to mark out the current, which is GM times VBE. And now, of course, in order to get that, we need to find out the VBE. Okay, so this is a very simple circuit. Because emitter is grounded, basically this circuit is divided into two separate circuits, even though in the middle they have the common ground. So on the left hand, what do you have? Two resistors in series. It is what do you call that? It is a voltage divider. So therefore, you can easily find VB equal to R pi divided by R pi plus so the left hand is the voltage divider. So that's what you have here. And the right hand is simply VO equal to minus GM VBE n times RC. Now we're going to plug in VBE to this equation. We got minus GM. We're going to move RC here. And VB is R pi plus so that's our final expression for our output. From here, we also can get the voltage gain, which is VO over VI to the minus GM. So we get the gain. So you guys can see what happens with the gain in comparison to the one and that we connect the AC directly to the base is the voltage divider over here. So the gain has just reduced this much. So at this point, I want to give you guys another concept. They say, if you look at the ratio over here, if R pi is very small and RB is very big, what happens? And this term becomes very small, which means your gain becomes small. So if your RB is small, R pi is big, and then let's say if R pi is 10 times bigger than RBB or 100 times bigger, basically this becomes negligible and your gain didn't change very much. So this is why when we have when you guys go to design a voltage source, you want the voltage source has minimum resistance, internal resistance, that's better. So but for the actual amplifier, a big resistance is good. Yeah. Which means the big R pi is good. Small R pi is not good. The gain of this circuit, because RBB is so big, like it's 100K, and R pi is something like 5K, so your gain is very small because that RBB drops so much voltage. Which means what happens is the voltage, VI, comes in, most of the voltage didn't go into the amplifier. It was consumed by RBB. So that's the reason. You consume too much internally within the voltage source. Okay. All right, so that's the equivalent circuit. And then, so now if you use the same example, and we want to say, okay, I want to have like a certain waveform come in and look at how does waveform look like at each node. Basically, we're going to draw it over here. So if VI comes in at a certain voltage like this, And apparently you can easily draw that IB, let's say this VI. So IB will be similar like this. Now, if you draw that IB plus IB, you know what happens? Right? It's going to be something like this. And then if we draw VO, and if you draw so this is like a VO plus capital VO. If you draw the small VO only, this is going to be like this. So that's what really it tells you that how waveform at each point. Just look carefully the flip of output in terms of phase from the input. The input is positive, output is negative. Input is negative, output is positive. So that's the only difference that point. Another point to note is that if you look at VO that I draw over here, the capital VO plus lowercase VO is the DC plus AC. For that one, you can hit the boundary. That's your output range. So like your bottom input cannot reach how much? You guys remember? 0.3 volts. And your up range cannot reach how much? Which is, yeah, ideally it's VDD, but it's going to be slightly less than VDD, but we'll temporarily put VDD over there. So that's kind of your output range. So if your waveform is moving out of this, like more than that, it's not going to work for you, okay? Now, sometimes let's say if your biasing point exactly in the middle, and you can get like a perfect, reach the boundaries at the output, but if your bias point is not at the middle, you could hit your boundary quicker on one side than other side.
So if my waveform was clipping, what would be the thing I would adjust to make it?
Well, depending, if you clip on one side, you can adjust your biasing point to move it up or down.
Let's say it was too big for both. Like,
For too big for both,
make it like smaller. Would I just like GM or something?
you need to make it smaller. Well, one of the things you could do, for example, you can add a resistance over here so that your input is not as big, right? That's one thing, right? Well, another thing that you can look at your GM, reduce the GM. When you reduce the GM means your IC, things like that has to change, right? Your GM is related, huh? Make it colder. Yeah, okay. So, so that's really simple. And then we're going to move on to, so this is what exactly just we show there. We have time for another example. Yeah. Here, this is our last example today. We're going to look at BJT, but this is P-type. So far with MOSFET and BJT, we've been focusing on the N-type. The P-type really, it's the same thing. It's just like you will get the same small signal equivalent circuit and things like that. The only thing that you pay attention is when you draw that circuit, like it flips D and flips D and S or C and E. That's all. That's all you have to pay attention. Of course, the current direction also changes. Remember for that NPN, the current goes into the base, but for PNP, the current goes out of the base. That's the difference. So for this circuit, we get a couple things to start. First of all, there are two capacitors, and we're going to short them for AC. But for DC, of course, we open them. So in order to get the actual gain, like what we did for the last example, we have to start doing the DC analysis so that we can get the quantities of IC. And then from there, we can get GM and R pi, right? So once you get that, and you move on to small signal, once we move on to small signal, we short the capacitors, right? But in this case, if you look at both the top and bottom emitter and the collector, they both have resistance. So naturally, you would use a T model. And again, I want to emphasize, there's nothing wrong to use pi model. It is just going to make your life a little bit more difficult. That's it. I mean, you can still solve it. It's just that the equation becomes more complex and it takes more time to solve the problem. It might make a mistake in the middle when you actually manipulate the equation. That's all. So use the T model in this case will make it simpler. That's all I want to say. All right. So first of all, we're going to start with the DC. As I said, with DC, you're going to remove all the capacitors. They're going to become open circuit. So in this circuit becomes very simple.
In both DC and AC, your capacitors?
When we
No, in the ACD.
when we do the DC analysis, the capacitor becomes open circuit. So that VI is gone, that VO is gone, so it's just this simple circuit.
That AC is at a high enough frequency that makes capacitors.
So
Capacitors are like, yeah, like.
so in this case, our base is grounded. Our base is grounded. So if our base is grounded, of course, we got to assume it's in active mode. Therefore, that VEB, so from here to here, we don't call VBE anymore, we call EVEB. So guys, you should be able to know what VEB is going to be. 0.7 volts. And so from here, we can find VE is going to be 0.7 volts. And you can find IE is going to be 10 volts minus VE divided by RE. That's 10 minus 0.7 divided by RE is 10. So you got 0.9, 0.93 milliamps. That's IE. So from IE, you can get IC, which is better. It's become like 0.92 probably.
Given data.
Was it given? If it's not given, you can assume it to be 100, I guess. Okay, so we got that one. So this is actually for the DC operation. Now from here, we can calculate R pi. Just can go ahead and do that. We can find these two values, R pi and GM, based on that IC, okay. And so now we're going to do the small signal. So this is the equivalent circuit from the original circuit to a DC. So when we do DC, I mean, from the original circuit to AC small signal. So when we get the small signal, what we are doing is we're going to like short all the capacitors. And then we'll also short the voltage source to ground. So now actually you have two grounds. One at the emitter, which is minus 10 volts, which becomes ground. And another one is that VCC 10 volts also become a ground. So this is our small signal model. So when you look at this, you know that this is a small signal model. This is not actual how a BJT would work in real life. You obviously have to connect voltage source here and there, okay? So the important thing here, of course, there's no need to do this step. You can actually do from there directly to a small signal, okay? So this step is not necessary. But sometimes students get like really good at doing problems. They don't do the small signal model anymore. They simply do this. They don't draw the actual like control current source, and so it's okay. I mean, as long as you can manage that, there's nothing wrong. You can do that. So what we're going to do is we can either use this one all that one, we're gonna do the small signal model, which again, as we said, we're gonna use the T model. So take this out. Look at the BJT over here. So we're gonna look at the T model, which at the E is going to be up. And then the B, of course, is on this side. And then we have a current source. The only thing that I think you guys to be really a little bit confusing, I think, is the direction of that current. In the NMOS, in NMOS, I mean, just make a little cutout here. So
This phone from the.
so in the NMOS, you have this. So that's why you have a pi model like this. And you have a T model so the current is going down that direction. So for BJT, the current actually goes this way. So the only difference is actually in the base. So the base current comes out of the base instead of going into the base. So for the NMOS is go into the base, but this goes out of base. And also the current goes from E to C instead of from C to E, right? So in that case, I mean, you can still draw like a current source like this. Or in the book, it's just up, which again, this is AC, so it really doesn't matter very much as long as you know what you're doing. When you actually mark the directions of current, like if I mark the current going down, the voltage across the RE is positive up, negative down, right? So, but if we mark it up, the voltage at RE also flips. It's going to be bottom up, positive, up, negative. So I want to explain this one here so you guys don't get confused. When you read the book, oh, why? Why is the current going up? It's, it's fine. Okay, so now we have our small signal equivalent model. So what we need to do is we need to connect all the components at each terminal. So we're going to start with the base. Where is the base connected? Ground. And okay, so what is the emitter connected? Emitter connected two things actually. So one is your RE to ground, and then the other one is your voltage source, right? Your voltage source is also connected to there. And then last, we look at where is the connector connected. The connector connected to RC to ground. And where's your output? Your output is a collector, is way over here. It says weird looking circuit, right? You're right. So the thing that confuses is to look at what is GM times VBE. Or in this case, you can also use like beta times IB.
Maybe just because like if they're all parallel, they all share the same.
Yeah, so
Voltage.
you just switch out VB for VI.
You can,
VI and then the voltage at VO is just that times the. Oh,
you can do that? You can do what?
well, okay, the volt, also it's not BE, it's EB.
VEB, yeah, VEB, right.
This talking is switched because N type.
Yeah.
And VEB just equals VI
VEB equal to VI?
because it's our B is ground
It's all parallel.
and we know that VE equals VI.
So yeah,
So it's 0 minus VI equals.
so B is grounded, right? B is grounded, and VI is also grounded on one terminal, the other one is
Yeah.
connected E. So your VEB is your VI, right? Okay.
And then our voltage at O is just the voltage across our resistor, which is our current going through our resistor times.
And your VO is going to be just your GM
Yeah.
times VB times RC. Now, in this case, is actually positive. So your gain, AV is VO over VI, is going to be GM times RC. So it's a positive. Remember, previously we got negative, right? Yeah, so here you get a really just a positive output.
Really large gain. Assuming GM is.
So this, what do you guys call this type of amplifier? What do you call this amplifier? Common what?
Common
Base. Yeah, common base.
I guess.
Yeah,
Base is grounded.
it's common base. Base is grounded. It's common base. Okay. Right. So again, the example is from the book, so you guys can go do the problem and then look in the waveform. And also, so this is what I just explained just a little bit earlier, saying, well, once students get really good at the circuit, they no longer have to actually draw the actual equivalent circuit small signal model. They simply assume that, yeah, this is my model. Why do I have to draw it? I simply can analyze the voltage and the current and so on. I know the equations, I can do it. So in here, what we're doing is, first of all, we find IB, and then we find R pi, and then we find IB to be like VI divided by this, and then we find IC, and then we find IO, and then we find AV. And this is basically the one that we saw earlier with RBB. Remember the one that we just had an example before the last example, right? So this is sometimes a simple procedure to do that. And this one, same thing. Like if you do the current analysis, so step 1, find IE. So IE is VI over RE. And then step 2, find IE. Step 3 is find IC is alpha times IE, goes here. And step 4, find a VO, right? And step 5, find AV here. So like if you plug this number, this is actually GM. So yeah.
Like, why do we do when there's like when there's a BJT with like a DC and AC? Why do we do DC first? Do we find something that helps us with AC, or what's?
Well, because you have to do DC, to find a GM and R pi and R pi. Yeah,
So we
or
do
RE.
DC
Yeah.
first so that we can find
Yeah.
those two, and then
And also often you do DC because you want to make sure it is in active mode.
inactive.
Yeah. MOSFET, same thing. You do DC to find it's in the saturation region. And then you find a GM and you find there's no R pi in MOSFET, but here you have to find R pi. But when you do circuit like this, we don't find GM anymore. We're just simply doing the relation of current and voltages. That's all. So this is like a simpler approach. But I don't like you guys to do this at this point at least. Maybe move on to 430, you can do that. Because in this case, if you do this, sometimes you got yourself confused a lot. So always do the graphical small signal model instead of doing this. But I just like one method you guys know it existed, right? Yeah, actually, we don't have time to do this example, but I want you to just conclude this section by you guys this is the process, like for NMOS and PMOS, find like the GM, which 2 times 90 divided by OOV, and RO is VA over something like you guys memorize that. And this equivalent circuit T model, and pi model and T model. And then for BJTs, there's a bunch of equations. I think for this, if you like keep these 2 slides in the exam, you should be able to have all you need in terms of equations wise, right? But of course, the circuit configurations needs a little bit of more effort to identify different things. So we're gonna stop here, and then next week, we're gonna look at different amplifiers and compare their properties and performance.
So the final, the final only covers.
The final only covers this chapter.
Oh.
Okay, great. See you next week. We do have class on Tuesday.
Yeah.
We don't have class on Thursday.
We do have class to do it. Well, there's only recorded anyway, so.
Is the final format the same as the term?
Yes.
So, open.
Yeah.
Well, actually, no, let's